Good morning or good afternoon, everyone, depending on where you are joining us. My name's Georgia Marchant and I am PR and social media lead at Fluke Reliability, home to eMain and Proof Technic. We have a truly special webinar today. So our speaker is Michael Leider. He's an electrical engineer at Advanced Energy, and he's going to talk to us about streamlining motor management practices. First, we've just got a couple of people joining, so I'll just let them get settled and then we'll get underway. Just wait for a few more joiners. Can see there's quite a few joining still. Awesome, cool. So I think we're ready to go and we can have other people join as we go through. So thank you so much for joining us for today's webinar, which is titled Streamlining Motor Management Practices to Reduce Energy Costs. As I mentioned, our speaker is Michael Leider. And before I formally introduce Michael, I'll just cover a couple of housekeeping topics. So today's webinar is being recorded and we'll share a link with you after the event, and you'll also be able to find it on the Fluke Reliability YouTube channel. So if you'd like to revisit the content or share it with someone, that will be accessible to you after today's session. As always, we do also invite your comments and questions. So you'll see a little questions chat box on your screen. If you think of a question for Michael at any point in the session, just type it in there and we'll either pose it to him at the end of the session or during, but probably at the end. Perfect. So as mentioned, today's presenter is Michael Leider. Michael has worked at Advanced Energy for the last 13 years, starting in 2010. And he started in the motors and drive laboratory before becoming a full-time engineer. So he's got extensive testing experience in the lab. He moved to a laboratory director role and then discovered his passion for motor system testing development, which includes research and training on a wide range of applications. He is also a member of the Advanced Energy Commercial and Industrial team, participating in energy assessments and recommending energy conservation measures at facilities across the Southeast. So, Michael, thank you so much for being here. And with that, I will hand over to you for today's talk.
Yeah, absolutely. Thanks, Georgia. And thanks again to the Fluke team, the Fluke Best Practices team, for giving me the opportunity to present today. And just to reiterate, if anyone has questions, we want to do the presentation. We also want to answer your questions if you have those. So submit those, as Georgia said, on the question window at the bottom, and then we'll respond to those. Hopefully some of the questions get answered during the content, but if not, we can run through those at the end. We're trying to leave about 10 to 15 minutes for the question and answer session at the end of the content. So today we're going to present on electric motor management and then energy savings opportunities. The information and the content is generally intended to help you develop or improve your motor management system in your facility. And then once you've improved the motor management system, move forward with generating those energy savings, finding the opportunities, and then implementing those opportunities to help your organization, lower electric bills, or in the event, most of our clients, you want, maybe a similar electric bill for more output, more product output. So help that for your organization, or maybe some are in the, foray into the consulting industry. Maybe you're looking to learn more about motor management to assist with your client projects. So first, I would like to say just a few words on Advanced Energy before we get started. So we may have worked with some of those on the line in the past, or maybe you've seen us on some presentations other topics or similar topics. But if you aren't familiar with Advanced Energy, I wanted to take just a moment to introduce ourselves. We are a nonprofit energy engineering firm based here in Raleigh, North Carolina, and we were chartered back in 1980 by the Utilities Commission in the state of North Carolina. Back then, we were charged to investigate and implement new technologies for distributed generation, load management, conservation, and energy efficiency. And over the last four plus decades now, we've worked closely with our clients as an independent resource for unbiased technical expertise in the fields of commercial and industrial, like commercial buildings, industrial facilities, manufacturing plants, and then also residential homes, electric transportation, motors and drives, and renewables. So that's a little bit about Advanced Energy. If you are interested more, I would of course invite you to visit our website. We have some nice videos and some great content on the website that we would love for you to take a look at. So why are electric motors important? So motor-driven systems are estimated to account for about, it really depends on what metric, different marketing studies have different numbers, but we estimate about 50% of all the electricity generated in the world is going to feed an electric motor. And motor-driven loads, if you're a facilities personnel, you're working in an industrial plant, in the audience, the motor-driven loads likely account for a large portion of that energy bill that you're paying. So having an effective motor management system and being able to take advantage of energy savings opportunities around those motors can definitely save you a lot of money over time. Maybe that's why you signed up for the webinar. I know this we're getting this one started in January, so no one's you're just getting started with your PDHs or CEUs. Sometimes we give these webinars at the end of the year, and people might be looking to get that last bit of credit for the year. But definitely, we'll look at opportunities where you can save money, improve process, and hopefully, generally upgrade your motor management system. So we're going to break it into two sections today. We'll start with the just general motor management, and then we'll go into those energy conservation measures and savings opportunities later on. One thing I did want to point out, the material isn't meant to be deeply technical. We do have a few good examples mainly at the end, but if you do have some deeper technical questions or application specific questions, I'm going to provide my email and phone number at the end of the presentation. Feel free to reach out to me directly. Email is best, but if something urgent, you could of course give us a call. So first off, actually, before we get into some of these numbers on motor management, I want to make sure that folks understand the motors that we're talking about, because I didn't provide any slides on this, but electric motors used in the facility, these motors that take in electrical power and then output mechanical power. So electrical input 480 volt, 240 volt, maybe if it's medium voltage, 2300, 4600 volt input, and then outputting some type of mechanical power, for some type of rotating equipment. So maybe powering or driving a pump, driving a fan, a type of fan, a blower, conveyors, very popular, need motors to drive them, crushers in your utilities equipment. So your boilers, your chillers, your air compressors, they're all going to have motors in there. Maybe in chilled water or boilers typically have motors that are drive with pumps that are driving water into or steam out or water out. With your air compressors, you have a motor that's driving the compressor itself. So those are the type of motors that we're talking about today. Some people call the motors or what drives your vehicle a motor. That's an engine, an internal combustion engine. Although you do have a lot of motors in your vehicles typically the windshield wipers, the power doors, power windows, excuse me. So there are a lot of motors in your car, your truck, your vehicle. If you do drive an electric vehicle, then you would have electric motors powered by the battery that drive the wheels, the traction motors. So those are the types of motors that we're talking about in your house. You have motors in your HVAC unit, your air conditioner, motors that drive the compressor and the condensing unit, or in your air handler, motors that blow air out into your house. So those are just a few examples. Your microwave, any kind of fan in your house is going to have a motor. So generally today we're talking about larger motors, three-phase power, the types of motors found in industrial facilities or larger commercial facilities. And again, sorry I didn't really include any slides on that, but I hope it's clear now kind of the type of motors that we will be discussing today. So here we have a few numbers to kind of get you in the mindset of the motor management and why it may be important to you. So the average motor is going to consume at least 50 times its initial purchase price in electricity usage over its lifetime. And then the second one, motor purchase price accounts for about 2% of the motor lifetime cost. So initial price that you pay is relatively small compared to the amount of electricity that machine is going to be using over its lifetime. Very small percentage is used for maintenance and upkeep, but of course, overwhelming majority, 98% is used for that electricity usage. Third bullet, less than half of the motor users consider energy costs in the repair versus replace decision. That's my estimate. Hopefully, whoever's watching the webinar, and I know we've got an on-demand version, hopefully that number becomes 100%. Take into account the energy usage, the electricity cost for your motor when you're making those repair and or recondition versus full replacement decisions. So due to these three things, and there are various other reasons, every organization or facility that uses motors should develop some type of guidelines or set of guidelines for managing the motor population. So what are the main components of the motor management system? We break it into three areas. So purchasing is the first one, and then operations and maintenance, and then lastly making that decision when you're going for repair or replacement. When you had a failed motor and you need to move forward with some type of fix or solution, are you going to repair it or are you going to replace it? So what are the benefits of the motor policy? So we put of course the money bags on the screen, but cost savings is a big one. Energy savings, and we'll get into that later on in our energy conservation measures section. And then increased production. So when your motors are running, process equipment is running, not having equipment downtime, all of that is kind of keeping raw products coming in and then finished products going out the door. Happier management for me, the less that I have to kind of push up to the people above me for continuing my facility to be running or keeping things going out the door, keeping products out the door means less pressure on me. So being able to develop some type of document or some type of specification so that when there is a motor failure, you're not kind of trying to figure it out at 2-3 o'clock in the morning. Whoever's on site, they know what the plan is for this specific motor or for this specific machine. So those four: energy savings, cost savings, increased production, and then shorter downtimes. So the next step, how do we create? We see the motor management system is valuable, and keeping track of the motors and the motor inventories. So how do we get that started? That's kind of the big thing that's tough for me sometimes, is where do I start with something? So first, we want to come up with some guidelines for those three main components. So for motor purchasing, it's very simple. You develop some purchase specifications, but what does that mean? Normalize which brands you use. We're product agnostic here at Advanced Energy, so we're not going to talk about specific brands or have conversations which brand is better than the others. I mean, really, they all have their pros and cons. It depends on your application. We get that question a lot. We have folks who tour our lab, who makes the best motor? Well, I don't think that's a one-off answer. So for you, in your situation at your facility, there may be a brand that fits your application better. Some brands may be better at crusher duty motors. Some may be better at marine duty motors. Some may be better at variable torque motors. So that's something that you need to decide for your facility specifically, and write that into your purchasing specifications. Also, if you have a great relationship with your motor distributor, they're likely licensed to sell a specific brand, maybe at a lower cost. So that's something else that you can consider. Once you've normalized those brands that you use, maybe it's one, maybe it's multiple, then specify model numbers for your specific critical machines or all of your machines. And then consider the life cycle costs instead of just the initial cost. And we're going to have a great example on that in the next slide. We saw earlier that 98% of the life cycle cost comes in, the electricity usage over the lifetime. So only 2% goes into initial costs, and it's kind of a difficult thing to get across, that all right, the amount that we're going to pay right now doesn't really mean that much because of the amount of money we may be investing over time. So having more efficient machines, more reliable machines, that's a lot more vital for something like an electric motor versus just looking at the initial cost. Another thing you want to do is purchase backups for your most critical motors. So these are machines where if this motor stops working, or this process machine shuts down, then you can't. The facility shuts down. You're not able to do that part of the process and then output product. So you want to have backups for those machines. Keep them on site, or keep them at your distributor if they're relatively close or if they're local. And then with those critical machines and backups, you can build up a spares inventory. So maybe you have motors that are used across multiple machines in the process that are the same. Storing one to serve 2 or 3 different machines would be ideal. The second step on creating the policy is operations and maintenance. And that's not really a topic that we're going to dive into too much today. We have other content that we can send to you on the operations and maintenance, but generally I will just say this: perform the routine maintenance on motors. So, whatever the manufacturer recommendations are. So recommended intervals for greasing and shaft rotation if the motor's sitting around in the inventory. If it has heaters like in the insulation, then turning those on every whatever, the quarterly or monthly, so that you don't get a lot of condensation buildup. For motors that are in use, then greasing, meeting the recommended greasing intervals, doing some temperature, capturing some temperature data on the windings, tracking that over time. Maybe doing a vibration analysis spectral analysis if you suspect that the machine may be getting close to failure or something like that. So we're not going to go too much on operations and maintenance. I would just say focus on focus on the critical motors with higher usage rates more for your operations and maintenance if you can. I mean, if you can, do all of them, but those are definitely the ones you want to focus on. And then the third step will be motor repair. So for the motor repair, I would use a repair shop that you trust. This is, something that's, you don't want to be getting stuff done at a shop and you don't have a great relationship with them. You don't feel confident in the work that they're delivering. So that's step one. I'd also recommend using a certified repair shop. So in the motor repair industry, they have third-party quality repair accreditations. We'll go over that. We have a slide on that in a second. But just like for purchasing, you want to develop the motor repair specifications and then use those specifications time and time again for the motor repairs. If you're using a certified shop, it's likely they'll create that repair specification for you because they're already following some type of specification. They can just document exactly what the specification would be for your motors if it needs to be a little bit different than some of the other clients. So I mentioned a few minutes ago we would have an example on life cycle cost for to kind of show that 2 to 98% numbers that I had mentioned. So this example compares the life cycle cost between a 75 horsepower electric motor and then a standard medium sedan. So a couple of metrics that are listed: the initial cost, purchase price of the car, the annual usage, so run hours for the motor, miles for the car, the efficiency, which is in percentage for the motor and then miles per gallon for the car, fuel cost, this electricity rate for the motor in kilowatt hours, and then price per gallon in gas, just regular unleaded fuel for the car, lifetime, and so yeah, lifetime. These are just kind of estimates. So once you take all of those variables, which I think we've made some reasonable assumptions on the variables, it's very difficult for this slide on the price of gas because depending on where you may be watching from, you may have different fuel prices. Also, the electricity price may be relatively different than what I've displayed. As I mentioned, we are here in North Carolina. So if you take all of those numbers and do the calculation, we have the annual operating cost for the motor at about $16,500, and then for the car, a little under $2,000. So the thing to point out is the initial cost of the car is 4 times that of the motor, but the life cycle cost for the motor is about 7 or 8 times that of the car. So what that adds up to is some pretty hefty electricity bills from the utility. And I'm sure you guys, if you are in energy management or involved in that, these massive bills that you may be paying just to run your facility. So you can see where some of these things that can be adjusted. Run hours you can't really adjust that. Fuel costs, you can't really adjust that. The thing that you can adjust here is efficiency. So having a higher efficiency is going to give you a lower life cycle cost for the same output motor. And next, I'm going to take a short break for a sip of water, but next we're going to dive a little deeper into each of those 3 components of the motor management system. All right, thank you. So step 1 is to create the motor purchase policy. So like we said earlier, standardize the purchasing, which makes it easier to order the products that you need, and it's going to save you a lot of time overall. The purchase staff needs to be properly trained, so initial cost isn't the only factor in that equation. Like we just saw from the example, the initial cost has very, very little impact on life cycle costs. And you see I keep repeating this thing. If you don't take anything else from this presentation, take that. That initial cost really doesn't play a major role in the life cycle costs for the motor. One thing that you can do in the purchase policy is pre-qualifying the vendors, and maybe in some cases you want to perform testing. Our motor lab here at Advanced Energy specializes in that testing. That's kind of world renowned for that stuff with various accreditations. I wanted to point to one example that we did for a recent customer. They were an original equipment manufacturer. They built conveyors, very like big, complex conveyors. You have a shipment that comes in, and then it directs all different ways as to which city or which region that those may be heading. So very big, expansive, long conveyors. Companies like UPS, FedEx, Amazon, they use these conveyors. So that conveyor manufacturer was looking to add some new motor vendors to the product line, or even switch. I can't say, but they contracted with our lab to test the incumbent motor and then various other challenger motors for various testing specifications to see which motors perform better for their specific application. And I can tell you the results were very conclusive for that equipment manufacturer. We only supplied the test results. We don't make any recommendations on which motors or which brands that you should use. And then they can take that information and combine it with their cost information to make a decision on which machine is better for them. So as I mentioned before, the second component, operations and maintenance, is not one that we're going to get into today in this content. So we'll spend a few minutes on the third component of the motor management system, which is motor repair. So step one with motor repair is to ensure the vendor, motor distributor, or repair shop in this case is providing the quality repairs. So here you see we have a picture of a motor with the rotor taken, end bells removed, and then the rotor taken out. So you can see when the repair shop is doing a repair, typically they're doing things like replace the windings. The windings are the copper piece with the plastic cloth wrappings around them, pulling the old windings out, installing new windings, and then not pictured, they will be installing new bearings, greasing the bearings, things like that. So similar to developing the purchase specification, you can develop a repair specification. So here we listed many items on the slides that can be added to those repair specifications. And like I said earlier, you definitely want to use the accredited repair shops. So many third-party quality repair programs out there, ESA accreditation, SKF certified, Green Motors Initiative, and even Advanced Energy. We have our own program called Proven Efficiency Verification. All the programs, have their own benefits. They're good. They have their own distinctions, but the goal of any accredited program is to ensure your motors are being repaired to the highest quality, and that same process is being used and standardized time in and time out every single motor. We have a quick example, where that wasn't necessarily the case on a motor repair. So this graph or the chart shows two performance curves. This is the same motor. It's a 10 horsepower motor. Nameplate full load efficiency for the motor is 91%. We see on the chart the orange line, which shows the efficiency when the motor was repaired with kind of top of the line bearing replacements and optimal, meeting optimal tolerances. Then we have the green or bluish green line below, which shows when the motor was repaired using bearings that were of lower quality. The grease amount wasn't right. The tolerances were a little off. So, there was a lot of higher kind of friction loss in the motor because of that. So you see just a simple, same motor, just a simple issue with the bearing installation causes a pretty distinct efficiency drop from the high quality repair to the low quality repair. So it's vital to make sure the repair vendor is not making mistakes like this one, or else you'll be losing a lot of money in the electricity cost when you put this repaired motor back into service. So one thing to consider with the repair vendors, they're happy to have your business, and they'll typically keep records for you for motors they've repaired or reconditioned, so they can help you with this management system tracking. Keep the open line of communication with the repair vendors. This failure history mechanisms, the vibration analysis, as I mentioned earlier, can be very helpful when you're tracking, like doing preventative and predictive maintenance. And then once you have your motor management system in place, keep track of the motor failures, track the energy costs versus production. So those are a couple of numbers you can use to update and improve the policy as you see fit. And this isn't just a one-time do-all exercise. This is something you want to be constantly improving to maximize the reliability and savings. And there needs to be someone in the facility, most of the time on the maintenance team or facilities operations team, who is kind of running this system. Once you develop the system, it takes the input of a lot of folks, but someone needs to be over the motor management policy in order for you to stay on track. So we have the summary slide. Once again, we'll state when you are purchasing the motors, use the life cycle cost instead of just initial cost. Secondly, develop and use the purchase and repair specifications so you get the best motors for your specific application, and then also the highest quality repairs. And lastly, utilize the strategic preventative maintenance techniques to upkeep your motor population and extend the useful life. So now we'll move into our second topic, energy conservation measures. So we'll focus on motor-related energy conservation measures for now. So what is an energy conservation measure? So these are really upgrades, retrofits, repairs, replacements, anything like that a facility could implement to become more energy efficient. How do we spot energy savings opportunities? So what I like to do is really take a look at the whole process, from incoming raw materials. Definitely, if you're an industrial facility, what's the incoming raw material, and then through to what's the finished product you ship out the door, and review every step in between getting that raw material to finished product. You're going to want to focus on your utilities, so compressed air, lighting, chilled water, steam, any other part of the process that's necessary to produce the finished product, but isn't necessarily the product itself. Those are where a lot of opportunities will be uncovered for saving energy. When should you make a change? Typically, we're looking for opportunities with like low payback periods. So we call it low-hanging fruit in this industry. Low to no cost implementation projects are going to be the best to kind of get the ball rolling. Payback periods less than a year, or no payback at all, or immediate payback. Those are the kind of things you may want to look for in order to kind of get your energy savings off the ground. Why would you make the change? Well, this may be obvious. You want to save money, you want to improve your process, you want to save time. Employee retention, that's another thing that's something to keep in mind for energy conservation measures. One example is like a cool roof. That's something that people may be familiar with. You install a cool roof on your facility. It keeps your roof cooler. Some facilities that may not have ventilation or have ventilation but not air conditioning in the summertime, the cool roof can help keep it a little bit cooler in that facility than if it didn't have one. So those are some other drivers for looking at different energy conservation measures. Once you have ideas for which energy conservation measures you want to pursue, a couple of steps you need to take are listed here: data capture and simple payback analysis. The simple payback analysis, you almost always need to do this in order to communicate whatever your idea is to others within the organization. An energy savings idea may sound great, but if you do the calculation and it's 10 years, then I wouldn't be spending too much time on that. Once you have the simple payback analysis and you have kind of a general idea, maybe you come to 2 years or 3 years. So it is good to do some metering and verification or data capture in order to feel more confident, have factual kind of evidence that you are going to be able to achieve these savings. And then once you make a change, it's also very good to do a before and after data collection. So capture some data of what the process is using before you make your upgrade, and then go ahead and take that extra step to capture, did you actually see those savings? Because the paybacks may turn out to be hopefully shorter, but in some cases longer than originally calculated. So with motors, I think the most common motor-related energy conservation measure is going to be adding variable frequency drives. Those who are familiar with motors, I think this is no secret. So that's where we're going to start. So number one, what is a variable frequency drive? So it's a device used to adjust the speed of an electric motor. You put, instead of going grid power directly into the motor, you go grid power connected to the input terminals of a VFD, and then from the output terminals of the VFD connected to your motor. The VFD can be used as the medium to control motor speed and motor torque by varying the frequency and voltage seen at those motor terminals. And if you're not familiar with variable frequency drive, you may recognize a different name: variable speed drive, adjustable speed drive, adjustable frequency drive, inverter, or just drive. So what applications work for variable frequency drives? So centrifugal loads, we mentioned a few earlier: pumps, fans, blowers, throttled flow processes, and variable processes. These days, air compressors have become kind of a good opportunity. A lot of times you can't just add a VFD. You have to, get rid of your older air compressor and then go with a new design which already has a variable frequency drive. Boiler and chiller feed water pumps typically are good opportunities. Fans all over the facility, and focus on applications with high annual operating hours, because when you have high operating hours, you have more time to capture the savings and offset the cost of that, installing that drive itself. Another thing is focus your time on like larger motors. Again, it's quicker payback and it offsets the initial cost. And once you've identified the motor applicants, dig a little deeper to determine the best candidates for the more in-depth analysis. So if you've done the motor survey or gathered inventory of the motors, which is that's the first step, that's what you want to do first, then a lot of that information will already be there. But if you haven't done that, get out in the plant, capture all your nameplate information, get it into a spreadsheet. Once you have the inventory, then look kind of estimated. Maybe you're the person who can estimate the run hours, or get with your team who can estimate run hours of each machine, or you can put some kind of meters on there and measure what are the exact run hours, how many hours a week or how many hours a month, and then multiplying that out if you want to do annual. to see kind of what are the best, what are the actual hours, then that helps you decide later on which are better applications for adding the variable frequency drives. My general recommendation is look at all the centrifugal loads with the operating times over 4,000 hours annual usage. So in the year we have, if you have a 24/7 facility, 24/7, 365 facility, you have about 8,760 hours. 4,000, that's about half the time, taking a couple of weeks here or there for plant shutdowns or holidays or things like that. So next, we have a couple of examples, 3 different applications where we're going to compare the validity of adding the variable frequency drive. So first, this one, you see the label is poor. We have percent operating time on the left side of the chart, and then we have percent rated flow or percent load on the bottom on the y-axis. Excuse me, x-axis. So this one is a very highly loaded application. So why shouldn't we add VFDs to the highly loaded applications? Because the VFD itself uses energy. So if you do put a variable frequency drive on a motor, and then that motor is running near full load, you're just going to add kind of unnecessary power to the circuit. And it's actually going to raise your electricity usage. So you tried to save energy, and then you actually spend more money, or using more energy, and you spent money to use more energy. It doesn't make sense. So adding the VFD doesn't make sense here because of the highly loaded application. The next slide, this is a moderately loaded application. So you see the load spending some time at 55%, 60, 65%, and then less time at the higher loads. So most of the operating time is spent around that 60 to 70% load. This presents an opportunity to slow the motor and capture some energy savings based on your affinity laws. And then lastly, we have the third example. This is the excellent candidate for a variable frequency drive. It's a moderate to low loaded application, some loading below 50%, but high operating hours overall. Great opportunity for significant energy savings. So next, we have an example. Once you've identified the good candidate for a variable frequency drive, how might you get some numbers for potential savings? So first, we start with some measurements. You're going to measure the baseline energy consumption and electrical demand of the motor without, it doesn't have a VFD at this point. And try to get that at each load level if it's pumping application or a fan that has a damper. You can find some way to calculate your output loads. Then you're going to calculate the electrical demand of the motor with the VFD using that same application load information. So you're able to slow the motor down in order to get that same kW output. Then you subtract your VFD kW, kilowatt demand, from the baseline demand at each load level and multiply the demand by time at each load level and sum over the entire load cycle to find the energy savings. Once you know those potential savings, then you need to determine that payback period that we've mentioned a few times. Get quotes from the service provider if you can't do the work in-house. Your VFD costs, including installation and programming estimates. Don't forget to include those. It's not just a plug and play, hang it on the wall, and then you're good to go. Estimate the electric rate. If you know the exact number, of course, that's better. In our area, for industrials, you're looking at 5 cents per kilowatt hour, up to like commercial and residential, you're in the 10 to 12 cents per kilowatt hour range. Then multiply your energy savings by your electric rate, and then divide your variable frequency drive initial costs, so including the programming and installation estimates. Once you divide that, that gives you your simple payback. Hopefully it's months payback, not years. When we go into facilities and we're doing these types of assessments and looking for opportunities, we ask, hey, what's your target payback? What's the maximum your management will be willing to listen to? 2 years, sometimes 3 years. In some cases, it's less, 1 year. But the longer the payback threshold, the more applications that are going to ultimately make sense for adding variable frequency drives. So next we have the short example we're going to run through showing that process I just described. So we have a water supply system pump, which utilizes a 75 horsepower energy efficient motor with a fixed diameter impeller. So it runs constantly 24/7 with the load cycle shown on the graph. Again, that's percent time, operating time on the y-axis, and then rated load on the x-axis. So you see a lot of time spent loaded between 40 and 70%, with smaller times loaded at 30% and then even less at the 80% load. So for the example, we've assumed a couple of things. Pump power is assumed proportional to the cube of the pump load. This is a reasonable assumption. And then VFD efficiency is assumed constant at 97%, also a reasonable assumption. So when we do all of the calculation at each, using the horsepower, conversion rate to kilowatt, and then time, run hours per year, and then efficiency for VFD, we get to a total of about 94,000 kilowatt hours per year. Then if we look, this one we did a little backwards of kind of how I'd originally said that. So we looked at usage with the VFD first. Then if we look at the motor demand calculation, so this is just motor itself, no VFD. The motor demand calculation using a similar calculation method, we see about 326,000 kilowatt hours per year. So doing the math, the 326 thousand kilowatt hours minus the 94,000 gives us about 230,000 kilowatt hours per year from our total usage. We've shaved it off. Using the electricity rate of 6 cents per kilowatt hour adds up to a cost savings of $14,000 per year. The payback period we haven't listed because we didn't include a price or a specific brand of VFD or anything like that. But I can tell you that at that rate, the payback is going to be less than 2 years, maybe less than 1 year, depending on what kind of price you can get from the distributor. Hopefully you see this and it gets you motivated to want to go out and look for opportunities in your facility. So what are a few other common motor-related ECMs? The motor management program, we discussed that and kind of in full. Replacing older inefficient motors with premium efficient designs, that's another one. Motors over time have they're in compliance, and if you're in United States, they're governed by the Department of Energy. So over time, they have just innately become more efficient as the government has required them, manufacturers, to build them more efficiently. You also have some motors that maybe aren't included in the scope of regulations that are more efficient because of the design type, newer technology motors, permanent magnet machines, synchronous reluctance, switch reluctance motors. You're going to pay more upfront for those motors, but the efficiency should be higher than your standard induction machines. Cogged V-belts on belt-driven applications, that's one that we recommend in every facility if you're using just standard. Belt-driven applications, a lot of HVAC, supply fans, or various other applications. Using the cogged V-belts gets you from a belt efficiency of 94, 95% up to like 97, 98%. So I know we have just a few minutes left. We did want to leave some time for the questions. I included a few bonus content slides. I'll go over those very quickly and then turn it back to Georgia. So Other ECMs, compressed air. I think this one is very common. Most facilities, industrial facilities, use compressed air. It's the most inefficient utility at your facility. Looking at electrical input into a compressor versus CFM output of your compressed air, it's going to be less than 10% efficient. So number one may be looking for ways to reduce compressed air usage. That's kind of where you want to start. One of those would be leaks, a leak survey. If you do have a lot of leaks across your facility, fixing those leaks lowers your compressed air usage, so it's going to lower your energy cost for using compressed air. If you can reduce the plant air pressure, that one's another one that's kind of an easy thing. You just bring if you're running at, if your highest use in the facility needs, say, 90 psi, and you're running your air compressors at 130 psi to output 130, then that can be fixed. You can just drop that down. Typically, I would say drop it down 1 or 2 psi. Like this, pick a day. Monday, I'm going to drop it a few psi, and then we'll see. I don't want it to cause any issues in the plant or any issues in the process. Drop it 1 or 2 psi, say each week or every 3 or 4 days, until you get to a point where you don't feel confident, dropping it anymore, or you've made it to that highest pressure required by process machinery out in the facility. And then a few others that you may be interested in: zero loss condensate drains versus, installing those if you are currently using timer drains. That'll save you a little bit. And then engineered nozzles. A lot of facilities use, definitely machinery facilities use blower nozzles to blow off your lathes and mills and whatever equipment. Switching some of those blow-offs to engineered nozzles can save you a little bit of energy. And then the last one, we're not going to spend too much time. I think my time is exhausted. Lighting. This is a great one where you can really start in the facility. Every facility needs lights. LEDs are kind of a slam dunk these days with the luminosity levels. In most cases, it can be a great replacement for if you have old, sodium lights, metal halides, or fluorescent T5s, T8s, T12s. Look at replacing those with LEDs. It's going to save you a lot of energy. And then if you prefer not to go for that full replacement, you can do bulb replacements into existing fixtures. Just make sure with your fluorescents, disconnect those ballasts. And then occupancy sensors, walking into rooms, leaving lights on overnight is just a very common problem. If you have occupancy sensors, you can solve some of those issues. Of course, the number one way to save energy on your lighting bills is just to turn them off. So that about wraps it up. If, again, like I said earlier, feel free to reach out to me directly for follow-up or general questions. And at this point, I'll turn it back over to you, Georgia. Thank you.
Awesome. Thank you so much, Michael. That was a really brilliant presentation, and thanks for the bonus slides as well. I'll remind everyone that we will be sending out the slides, and you can also access this on our YouTube channel after this. So if you want to sink in and just go over what Michael said, you can absolutely do that. We do have a couple of questions that have been submitted. If you do have a question that you've not yet submitted, if you could just pop it in the Q&A chat box now, and we'll try and get through as many questions as time allows. So the first question is, I have investment dollars to make energy improvements at my facility. Which upgrade should I pursue first?
Yeah, that's a good question. It depends on the facility. I think that I hinted at this on the last slide. The lighting is something that's generally a slam dunk. So that may be the area you want to start with. Or if you have compressed air, that's another one, because it's just innately so inefficient. But if you haven't made upgrades to LED lights, that would definitely be the place to look at first.
Fab. And then how is best to assess or estimate motor efficiency on site with minimum resources?
Yeah, that's a good question. It's very easy to measure input, but not so easy to measure output, torque and speed. So the way that we would kind of look at motor efficiency for an estimate is the nameplate efficiency. That's not a great way to do things. More importantly, it might be percent loading. So if you have a motor that has on its nameplate, say 50 amps, if you measure when take your terminal box, do this safety first, of course, but you have your terminal box off, and then you're measuring with an amp meter what is the current coming into the motor. If you have 33 amps, then you know that you're only 66% loaded based on that 50 amp rating. If you have 50 amps, well, you're pretty much fully loaded. So probably not a great opportunity if it's sitting close to that rated amperage most of the time, but if it's lower than that rated amperage or significantly lower, most of the time, that's the area you want to look for energy savings opportunities. Efficiency, I think for now, if you don't have like a test report or test data, just use that nameplate efficiency, but understand, your running efficiency may be less than the nameplate efficiency. It could be more, but generally it might be less than that efficiency. And if your motors have been repaired or something and not using a good process, you could be significantly below that nameplate efficiency.
Awesome. And then we've got another one here which says, when we talk about purchase policy, how important is initial sizing of motors? So our audience member says, in my experience, in quite a few cases with different safety factors, motors generally operate at about 50% loading, 50% loading percentage.
Yeah, it's quite a interesting phenomenon in this industry that in most cases, when you're doing purchasing, the application may call for like a 20 horsepower motor, but then installed will be a 25 or a 30 horsepower motor. And that's because as facilities engineers, we may be worried about failing the motor. So we want the motor to run for a long time. We are less concerned with energy costs at times, more concerned with keeping the site up and running. So that's kind of where that comes into play. If you install a motor that's significantly oversized, it presents a great opportunity for energy savings by installing a variable frequency drive. So it's one way to deal with oversized motors is by, if you don't feel confident to use the appropriately sized motor, that would be my recommendation, is if you have an application that calls for 20 horsepower, use a 20 horsepower motor. But if you are going with that larger motor, so the motor is running at lower than full load the majority of the time, it's going to show up as a good energy savings opportunity to add a variable frequency drive.
And then we have another one, which was, what are the advanced preventative maintenance techniques for motor?
Yeah, there's a lot, and I think there's a lot of great vendors in this industry that will be happy to broadcast. I don't know, maybe they've given some presentations before with you all, but mostly you need to keep track of some things. Temperature, so current, what is the motor actually running at? If it's over its rated load, or if it's over its service factor load, the motor is going to fail quicker. If it's running below its rated load current wise, that's a good sign. If you see the motor start to really heat up, you can use an IR infrared thermometer to find hot spots in the motor windings. If you start seeing those hot spots, if you're doing like a quarterly maintenance program or monthly maintenance program for your critical machines, you're going to see these hot spots start to show up in the windings, and then you kind of are able to then predict or prevent failure and make change outs during planned downtimes versus that becoming a downtime. And then the last thing is vibration analysis. That's the more advanced. Those are kind of the three things that I would say on the advanced preventative or predictive maintenance techniques that I would focus on.
Awesome, and I know that kind of brings us up to time, but one of our audience members has asked if you are able to share the spreadsheet for calculating the savings potential for motor to VFD.
Yeah, absolutely. I think take my email address, and if you want to just send me a message, I'll be happy to do that.
Fabulous. Well, thank you so much, Michael, for sharing your insight and expertise there. You've got some really nice comments in the Q&A box as well. Do you have any comments that you want to make in closing?
No, I think great. Thanks for having me, and look forward to the next opportunity. Awesome.
Thank you so much. And thank you to everybody that joined us today. There will be a brief survey, which is just 6 really quick questions. It'd be really great if you guys could fill that out, because it just helps us to improve these webinars. And if you have any additional questions or you want to connect directly with us, you can either reach out via our website or on LinkedIn. Thank you so much for your time, and have a wonderful rest of your day. And thanks again, Michael. Bye.